Hello friends, I welcome you in lecture number 15 on complex differentiation. In previous lecture we have discussed one property of analytic function, and that property was if function f of z is analytic in some domain D, and if absolute value of f of z is constant in domain denoted by capital D, then f of z is also constant in that domain D. In this lecture also we are going to discuss two more properties of analytic function. First property is that if our function is analytic in a domain D, then f of z is constant in domain D if f dash z vanishes identically in D. What is meaning of this? F dash z vanishes identically in D. That means value of derivative is 0 for all points z in domain D. If f dash z equal to 0 for all points in a domain D, and if f of z is analytic in a domain D, then also f of z becomes constant. So we are going to prove this property, and first we write that it is given that f of z is analytic, given that f of z equal to u plus iv is analytic in domain D. And because f of z is analytic in domain D, it is differentiable at every point in domain D, and we know that if function is differentiable, then its derivative is given by del u by del x plus I into del v by del x, and this is for all points in domain D. And what is other thing is given f dash z is 0 for all points in domain D. It is also given that f dash z equal to 0 for all z in domain D, and f dash z is nothing but del u by del x plus I into del v by del x equal to 0 in a domain D. And this is possible if and only if del u by del x equal to 0 and del v by del x equal to 0 in domain D. And using cauchy-riemann equations, we can write del u by del x equal to del v by del y, and we can use another cauchy-riemann equation, which is del u by del y equal to minus del v by del x. Therefore del v by del x is minus del u by del y equal to 0, and that means del u by del y equal to 0 in domain D. So here we are using that f of z equal to u plus iv is analytic in domain D, and therefore it is differentiable in domain D. Therefore CR equations are satisfied in domain D. So we can use ux equal to vy and uy equal to minus vx in domain D. So using that, we find that first order partial derivatives of u and v are 0 at every point in a domain D. Therefore what we obtain, ux equal to 0, uy equal to 0, del v by del x equal to 0, del v by del y equal to 0 in domain D. And this too implies that u is constant in a domain D, and this implies that v is constant in a domain D. And if u and v are constant, then f of z equal to u plus iv is also constant in domain D. So what we have proved? if function is analytic in a domain D and if derivative of function is 0 at every point in domain D, then f of z is constant in a domain D. If you recall the calculus of real functions, if you have understood this thing in real function or in calculus, we know that if we have function of one real variable denoted by f of x, and then we know that if f dash x equal to 0, then fx is constant. So here also we have same result. Here we have f dash z equal to 0 implies f of z equal to constant, and here we require that f of z is analytic in a domain D. Here we require that f of x is differentiable in some interval or in some subset of the real line. So both are similar results, or we can say that analogous result. In calculus, if f dash x equal to 0, then fx is constant. In calculus of complex functions, if we have analytic function whose derivative is 0 in a domain D, then f of z must be constant in a domain D. I have taken another property which also we will prove. Here it is given that if f of z and conjugate of f of z are both analytic in a domain D, then prove that f of z is constant in a domain D. So first we consider f of z equal to, say, u plus iv, and given that f of z is analytic in a domain D, first we write that f of z is analytic in domain D. Therefore, u and v must satisfy cauchy-riemann equations in a domain D. Del u by del x equal to del v by del y, and del u by del y equal to minus del v by del x in domain D. Now if f of z is u plus iv, then conjugate of f of z will be equal to conjugate of u plus iv, that is u minus iv, or this we can rewrite as u plus I into minus v. And suppose we assume that this is equal to capital U plus I into capital V. Suppose this is equal to capital U plus I into capital V, then we find that capital U equal to small u and capital V equal to small v. Capital U is real part of f of z bar and capital V is imaginary part of conjugate of f of z. Now it is also given that f of z bar or conjugate of f of z is also analytic in domain D. Therefore, real and imaginary parts of f of z bar will satisfy cauchy-riemann equations. Here we have capital U as real part of f of z bar. So instead of small u and small v, we have capital U and capital V as real and imaginary parts of conjugate of f of z. So CR equations will be del u by del x equal to del v by del y, and del u by del y equal to minus del v by del x. And now capital U is equal to small u, therefore we have ux. Capital V is minus of v, so this is minus vy. We are writing del v by del y, that will become minus small v with respect to y. Similarly, u equal to small u, therefore del u by del y equal to small u with respect to y. And vx, here we have minus vx, so if we take minus if we multiply both sides by minus 1, we have minus v equal to v, and if we differentiate both sides with respect to x, we have minus vx equal to small vx, and this is also true at every point in a domain D. And now we are going to use these equations to prove that f of z is constant. So you can concentrate here now. Here we have ux equal to vy and uy equal to minus vx. Here we have ux equal to minus vy and uy equal to vx. And if we wish, we can give numbers also. I can denote this equation by number 1. This I can denote by number 2. Suppose we consider this as number 3, and suppose this is given number as 4. Now we concentrate on 1 and 3. Equation 1 is ux equal to vy and equation 3 is ux equal to minus vy. So we first add equation number 1 and 3. Adding 1 and 3, we get left hand side is ux, so we have ux plus ux. Right hand side of 1 and 3 is del v by del y and minus del v by del y. So let me write one more step. So what we obtain, therefore 2 times ux equal to 0, and because 2 is non-zero, ux equal to 0 in domain D. Similarly, we add this equations number 2. Here we have uy equal to minus vx and here we have uy equal to vx. So if we add 2 and 4, adding equation number 2 and 4, we get, here we have del u by del y on the left hand side, and on right hand side here I have minus vx and here I have plus vx. So here I write minus vx plus vx. Therefore we have 2 times del u by del y equal to 0, and this implies del u by del y must be equal to 0 in domain D. So we have shown that first order partial derivatives of u with respect to x and y are 0 in domain D, and this implies that u must be equal to constant in domain D. Now f of z is analytic, therefore we have using cauchy-riemann equations, we can write ux equal to vy, so that is also 0, and uy equal to minus vx, so minus vx is 0, that will give me vx equal to 0 in D. Here we are using the fact that f of z equal to u plus iv is analytic in domain D, therefore CR equations are satisfied, ux equal to vy, uy equal to minus vx. So I find that del v by del x is also 0 and del v by del y is also 0 at every point in domain D, and this gives me v must be equal to constant in domain D. So we have shown that u and v are constant in a domain D, and therefore f of z is also constant in a domain D, because u and v are real and imaginary parts of f of z, and therefore f of z is constant in a domain D. So this is very nice property. It says that if function and its conjugate are both analytic in a domain D, then f of z is constant in a domain D. And what we have used just Cauchy-Riemann equations. First we use the fact that u plus iv is analytic, and we write down one set of Cauchy-Riemann equations. Then we use the fact that f of z bar, that is u plus iv, is analytic, and we obtain another set of equations. And using all these equations 1 and 3, we find that ux and uy are 0, and then using Cauchy-Riemann equations, we find that vx and vy are also 0, and that gives us that u and v must be constant, and therefore f of z is also constant in a domain D. So we have proved three properties. First property was that if absolute value of f of z is constant and f of z is analytic, then f of z becomes constant. Second property is if f of z is analytic and if derivative of f of z is 0 for all points in a domain D, then also f of z is constant. And third property we have proved is if f of z and conjugate of f of z are both analytic in a domain D, then also we have shown that f of z is constant in a domain D. And in all these proofs, we have used the fact that function is analytic and therefore it is differentiable, therefore CR equations are satisfied. All we are using is CR equations because of analyticity or differentiability. So this is all about this session. I hope you like it. Thanks for watching.